Hey, Dr. Clark here again with another stats video. In this one, we're going to learn how to do inference for linear regression. In the last one, we learned how to create a linear regression. Now we're going to do statistical inference to see if that regression we found, if the pattern we found is statistically significant. Let's take a look. So inference for the slope of a linear regression. Okay, and we're going to use a simulation-based approach. So the idea is when you do linear regression, you have some observational unit and you measure that unit with two quantitative variables. In this example, each of these is a hike, and that hike has a distance and it has a time, right? So this hike was 6 miles long and took 180 minutes to do, something like that, right? The scatter plot of the data shows you whether there's a relationship, and you can see the longer the hike, the longer the time it took it, right? But it's not like a perfect line. I mean, this hike was 6 miles and took that many minutes, and that one was 6 miles and took the same, a different amount of minutes, right? But we're trying to see, is there a general pattern in the data, and the linear regression line models the general pattern that we're seeing. Okay, it's not going to be a perfect fit because data is not all perfectly linear, but we're looking for the general trend. So if we knew the explanatory variable, we could multiply by the slope, add the y-intercept, and that would be the predicted response variable. So if somebody said, hey, I got a 6-mile hike coming up, how long do you think it'll take? Well, if I had a regression line, I could say, well, it probably will take about 200 minutes or something, right? I could make a prediction based on knowing the x value, the value of the explanatory variable. All right, what we're going to do is do inference on the slope of the regression line. If the data has a pattern to it, then there should be some slope, right? There would be a slope to that line. If the data is just randomly mixed around, then the slope of the regression line would basically be 0. So that's what we want to know. Is the slope of the regression line 0 or not? And what you got to understand, and this is the key concept, is the data you have is just a sample of data, and that gives you a sample regression line. What we're really interested in is the true population of data, which would have a true regression line. So sure, here's 72 different hikes that we could go on, but if we went on every possible hike and maybe every possible person in the world, maybe, I don't know, it kind of has to depend on the data. Maybe this is me, maybe every one of these hikes is me, and it's just 72 different hikes, but maybe there's 2,000 possible hikes I could go on, and these 72 are just a sample of the 2,000 possible hikes I could go on. And so there's a difference between the population data and the sample data, right? We're only going to have a sample of data, and we're trying to figure out, is there a true regression line? Of course, we'll never know because we would never have the full population. But if we did, there'd be a true regression line. What would be the slope of that regression line? Of course, we don't know what it is, but we can estimate it using what we see in the data. So if you want to imagine it, let's say here's 72 total possible hikes I could go on, but you only have this sample of 14 of them over here. Well, based on this sample, you would say, oh, okay, sure, there's some pattern here. I can make a regression line. But the true pattern is over here in this population data. That's the idea. There's some truth going on, and our sample is trying to help us get at the truth. In the notation, when we have sample data, the correlation is R. When we have population data, we talk about rho, which is the true long-run correlation. If you had the true population data, that would be the long-run correlation. In the sample, we just call it R for correlation. The linear regression in the sample, we have y hat equals a plus bx. In the population, it's y hat equals alpha plus beta x. And beta is the true slope, and that's what we're going to do regression on. A is the sample y-intercept. Alpha would be the true y-intercept in the data. When you run a hypothesis test, the null hypothesis would say there's no association between the two quantitative variables. The alternative would be that there is an association. We're trying to show that there is an association if there is one. In terms of our statistics, well, the true slope of the linear regression, that would be beta, right? The true slope. That would be 0 if there really is no association, and it wouldn't be 0 if there were an association. And you could do a one-sided test if you wanted to do greater than 0 or less than 0, but generally we do two-sided. So this is the general idea. When there's a pattern between the distance and the time, then we see a slope in the data, right? So the true data would have some slope beta. If there was no pattern, then these dots would just be mixed all over, and the slope would basically be 0 when you did the regression line. So that's how the hypothesis test works out. Okay, so that's the main ideas we're looking at. And in the next video, we'll do an example problem. So we'll see you there.